Alright, so we're going to look at the case of an attractive delta potential near an infinite wall. Alright, so it's like half of an infinite square well, but then we have an attractive potential here on this other, at this point of x equals a. Alright, so one thing to notice real quick is that we have this extra a into this as part of this potential here. Alright, so V naught is, well, I guess V naught multiplied by A is sort of the strength of the potential. So because it depends on A, the further we move away, the stronger this potential gets. So what this does is it just, I guess it just makes the x dimension, alright, because the x dimension part that matters is the distance between the potential and the wall. So it makes the x dimension and the y dimension, the only part of the y dimension that matters is this potential of this strength, right? This part is infinite and the delta potential is infinite. The strength is all that matters. So it makes the x dimension and the y dimension scale the same. Alright, so basically this problem will scale up, scale down, and because x and y are scaling the same, we don't have to worry about that. Okay, alright, we probably should start with the Schrodinger equation. Okay, so here we go, our Hamiltonian, this is a time-independent Schrodinger equation. Multiplied by a wave function will give us the energy multiplied by the wave function. V squared over 2m plus v. Okay. And then we have a minus h bar squared over 2m, and our second derivative with respect to x. All right, putting in the momentum operator. Okay, so I'm going to subtract v from this side, so we get an e minus v, but then we'll have this minus sign here. Well, let's just leave it there. Alright, we'll leave the minus sign here. So alright, so here we go. We're going to be looking at a bound state, right? So that tells us that our potential is less than less than 0, basically, negative. Alright. Alright, so if v is 0 for most of this, so what we're going to do, anyway, this will end up being what? Being positive, right? So maybe I should have gone ahead and switched this. Okay, so B is less, excuse me, E is less than V, so that this is positive. Alright, so for positive values here, we're going to tend to get things that either shrink down to 0 or blow up. So the general form of our wave function let's just start off using A and B. Alright, we need to define this real quick. So I'm just going to use K pretty standard k squared for this, right? Okay, so this is positive. K squared is positive. All right, so we're going to get e to the kx plus a term e to the minus kx. All right, so here we go. So now what we need to do is meet our boundary conditions for this problem. So let's go ahead and work out the little boundary condition here at the delta potential. We know there's a boundary condition right here where the wave function must go to 0. So I'm just going to write this one out real quick. Okay, wave function must go to 0 at an infinite wall, because it's not infinitesimally thin like this delta function is. Okay, so let's go ahead and work out our little delta function condition here. So we'll start up here at this Schrodinger equation. Okay, and we're going to integrate it from, I will say a minus epsilon to a plus epsilon. And we'll end up taking the limit as epsilon goes to 0 of this whole expression. All right, and the first part is this double derivative here. Okay, and then let's go ahead and plug in our potential. So we'll have a minus sign from right here. I'll go ahead and write our integral right here. And we have a v naught a delta function x minus a. Okay, and so there's our potential. Now we need to put in a c for our wave function. Integrate with respect to x. Okay, and then finally we have a minus epsilon to a plus epsilon of e c dx. Okay, and this is all as we take the limit of epsilon going to 0. So what we get here is minus h bar squared over 2m. All right, and then we're going to have the single derivative. All right, this integration took out one of them. Okay, so we're we have this, but then we're evaluating it at these two limits of integration. So this one's evaluated at a plus epsilon, and then we have to worry about this bottom limit of integration, a minus epsilon. Okay. All right, now here we go. We are integrating over x equals a, right? Plus epsilon minus epsilon. That's kind of the whole point of this, is just so we can include this delta function right here. And all right, so what I need to do is, so this will integrate to 1, except everything is going to be evaluated at x equals a. So that I guess maybe I should write a little parentheses x here for this c, so we know that it's a function of x. So anyway, what we get this, which, and these are just constants, right? This integrates to 1, but we have to evaluate our wave function at the point x equals a. All right, and then for this final term, there's this integral is, as we take this limit of epsilon equals 0, it's becoming very, very thin, and there's no infinite delta potential inside this one to give us anything. So this integral is just going to go to 0. All right, so I mean, I guess, yeah, anyway, it's just 0. All right, so let's go ahead and write this out real quick in maybe a nice form, which is just rearranging it. I'm just going to go ahead and call this a plus. And a minus, because all we're doing here is evaluating, this is just setting up our boundary condition on the derivative of the wave function at this point. Normally derivatives are continuous, except in the case of this discontinuous potential, but the value of the derivative on one side and the value of the derivative on the other side are going to be related by this. All right, so this is just the derivative of our wave function on this side of the potential, like right at the delta function, and then this is just the derivative on the other side. Okay, so it looks like we're going to bring this over, get rid of this minus sign, but we've got another one waiting for us. Multiply both sides by 2m. We have our v naught a, c evaluated at a, and divide everything by h bar squared. All right, so this is, these are our two boundary conditions. All right, one of them is right here, and the other one is right here. All right, so using this, we're going to solve for this equation. All right, our end goal here is we're going to solve for the energy of a bound state, and we're also going to, what was it? It was, oh yeah, what is the minimum value of this v naught right here, which will give us a bound state. So if this potential, this delta function isn't strong enough, then it won't hold a bound state. So, all right, let's go ahead and divide this into regions. We'll just call, let's just call it region 1 and region 2. Okay, and that division happens right at x equals a. All right, so the wave function will have a form like this in each of these two regions. Let me just, I'll just reuse these constants here. So a e to the kx plus b e to the minus kx, and then for region 2, let's use c and d. Great. All right. So let's see what we can learn about this. So for one thing, if we look at this region 2 here, we know the wave function has to go to 0 out at infinity. So this term has to go away for our wave function to be normalizable. So we'll kill this. C is equal to 0. All right, what else do we know? Well, all right, let's work on this boundary condition right here. So that pertains to C1, right, which is our little piece of the wave function in this region. This one presumably doesn't even know about this wall here, except when it comes to normalization or something. So here we go. We're looking at this boundary condition with respect to the wall. So here, that just tells us that C1 at x equals 0 is equal to 0. So that means we have, when we put 0 in for this x and this x, these exponentials just go to 1. All right? So a plus b is equal to 0, or a is equal to minus b. All right, so we can rewrite our equation for C1. Let's go ahead and write it on a new sheet, which is, once we know this, we can kind of, we just put a minus sign in here and factor out the a. So what we get, so we factor this out, we get an e to the kx minus e to the minus kx. All right, which this is just hyperbolic sine divided by, or multiplied by 2. All right, so I'm going to take the 2 out of this, and let's just combine it with this constant out here, and just to be strict about this, let's give that constant a new name of f, since we've gone through. We don't want to use e because that's energy, right? Hyperbolic sine of kx. All right, so here's an expression. Now we're down to just one unknown constant for region number 1. All right, so now let's look at our second boundary condition here, which is a condition on the derivative. All right, so if we look at the a plus situation, that pertains to psi 2, and a minus pertains to psi 1, because those are the wave functions just barely to the right of this and just barely to the left of this. All right, but they do need to be evaluated at the point a, x equals a. So here we go. A plus, we'll take the derivative of this, so we get a minus k d e to the minus k. All right, and then we're going to evaluate this at x equals a. So there's an a right here. All right. Now we will take the derivative of this. All right, and let's go ahead and use the new form that we found real quick. Okay. So this, when we take the derivative of this, we'll just get a k, and then we have our f, and then hyperbolic sine turns into hyperbolic cosine. And again, we're evaluating at x equals a. Okay. All right, so another condition that we have to meet is that at this boundary here, even though the derivatives may be discontinuous, the wave function itself must be continuous. All right. So this just tells us that when we go and we put in this side here, we can pick either one of our, we can pick psi 1 or C1 or C2 to put here. Obviously, we're going to go with the easier one. All right, so we have a minus 2m v naught a over h bar squared. And then we've got, we're just going to put in C2 because it's simpler. All right, so here we have an additional constraint on our equations here. All right, so let's see what we can do. What we want to end up doing eventually is we want to solve for k, because when we look back at where we defined k, this has the energy inside of it. So once we solve for k, then we can solve for the energy. All right, so that's our first goal. All right, so to simplify this a little bit, we can just take out these minus signs. Yeah. All right, so this is one of our equations that constrains our wave function. Like we talked about, the wave function itself must be continuous. So our C1 at A must equal C2 at A, so that will give us another equation. So that one is, so we have our C1, which is F hyperbolic sine, and then we have evaluated at A, so KA, all right, is equal to this C2 here, also evaluated at A. All right, so now we can use these two equations together and hopefully eliminate our some of our variables here. So we want to clear out these constants is kind of what we want to do. All right. So how should we do this? Let's take. What should we do? Let's solve for f. Okay. So f is equal to d e to the minus ka divided by hyperbolic sine of ka. And now we'll plug this in up here. Okay, so we'll write out our whole equation down here. We have k d e to the minus ka plus k. All right, so now I'm plugging in this f here, d e to the minus ka, and then we'll have a cosh over sinh, which is a hyperbolic cotangent evaluated at ka. And then on this side, we just have a 2m v naught a over h bar squared d e to the minus k. Make sure, did I need to evaluate this? I did, didn't I? This should be an a right here. I think I must have just got ahead of myself. Okay. Make sure that's right. I think that's right. All right, so obviously we can come through here and just divide out these three terms. So we have a k1 plus hyperbolic cotangent ka equals 2m v naught a over h bar squared. All right. So, I don't like dealing with hyperbolic cotangents. Let's multiply both sides of this by a hyperbolic sine. Okay, so that will give us a hyperbolic cosine here. And we were multiplying by hyperbolic sine. So here we go. There should be another parenthesis there. Okay. Let's go ahead and work this out real quick. Hyperbolic sine is e, or this would be e to the k a minus e to the minus k a divided by 2 plus e to the k a plus e to the minus k a divided by 2. All right. So these two are going to subtract out, and half of this plus half of this equals the whole of it. So e to the ka is what we've got left. All right, and on this side we have a 2m v naught a over h bar, and let's also go ahead and split this up. So we would have an e to the ka minus e to the minus ka divided by 2. These 2's are going to cancel. All right. Now we will, let's just divide both sides by, we're almost there, here's our k, right? So m v naught a over h bar, oh, I left out, okay, this needs to be an h bar squared. All right, count myself lucky, I caught it fairly soon. See if anything else is wrong, who knows. All right, so here we go. All right, so this is an expression for k, and we know that if we go back to our original use of k, right, that it is equal to this, k squared is equal to this, right? So if k, so once we take the square root, we'll have a 2mv minus e over h bar. All right. And so, solving this, so we are going to have h bar k, so momentum, right? Momentum squared over 2m. All right, and then v, right, for all of this, where it actually matters for the energy is going to be 0. All right, so let's just leave it at that for now. All right, so to solve for the energy, we would just take this big old thing here. Well, let's just do it, fine. Let's just do it. We're just going to plug this big thing into this. All right, so we've got 1 over 2m. We'll have an h bar squared. Let's plug in some of these constants real quick, because we're looking, anyway, we'll be squaring this, right? So m squared v naught squared a squared over h bar to the 4th, and then a 1 minus e to the minus 2 ka squared. All right. Just check this real quick. Oh yeah, so a few things we can do. We can divide out this m. We can get rid of some extra h bars. So m v naught squared a squared over 2 h bar squared, and then 1 minus e to the minus 2 k a squared. So there we go. Here's our e. All right, so now if we want to ask ourselves the second question, which is, in order to have a bound state, how strong must the potential be, right? So what is the minimum value of V naught, which will give us a bound state? All right, so this occurs, all right, when E well, okay, so basically K is going to be very, very small. All right, so I guess the point at which this V naught is strong enough is also the point when K is equal to 0. So we can't just solve for, let me go back to my equation for K, wherever I put it. All right, this one. All right, we can't just plug in a 0 here, because then this would give us a 1 minus 1, which is equal to 0, which doesn't tell us anything. All right, so let's go ahead and do a Taylor expansion of this equation. I guess mostly just this term right here, right? So we're imagining, we're looking at the region where K is very, very small, just to see, you know, as K approaches 0, what does V, if we solve that for V naught, what will we get? All right, so here we go. We'll have K on this side equals m V naught a over h bar squared, and all right, so now we're going to have on this side a 1 minus, all right, so we're going to just take the Taylor expansion of our exponential term right here. All right, so when the Taylor expansion of an exponential is going to be a minus 2ka, so just what's up in the top, right, to the 0 over 0 factorial plus minus 2ka over to the first power over 1 factorial. All right, so we'll only keep the first two terms, but this goes on and on and on. And I need one more parentheses. Okay. So we have an m v naught a over h bar squared, and then here we have a 1. All right, minus. All right, this piece right here to the 0th power is going to go to 1. All right, and then if we look right in here, we have another minus sign. So minus and a minus will give us a plus 2ka, and then divided by 1. All right, so this just equals 2ka m v naught. Let's see where my paper ends here. V naught a over h bar squared. All right. So now looking at this piece and this piece, the k's will divide out, and then h bar squared will end up. If we're solving for v naught here, h bar squared will end up on the top, and we'll have a 2a squared. There are two a's here, right? This a and this a. So 2a squared, and then we have an m. All right, and we've just solved this So K equals this. We've solved that for V naught. And so here we go. So this is the minimum strength that this attractive delta potential must have. Remember, however, that we did, usually when you define a delta potential, I think usually, right, there's no A here, right? It doesn't depend on the X, right? So again, we've rendered the problem scaleless with that. But we must have at least this much strength in the delta potential well to be able to hold a bound state. So you can see that depends on the mass. It also there's also this a squared here, right? So yeah, I mean, maybe we still do end up with some dependence on A, because A squared is not going to cancel with this A up here, and then of course H bar. So anyway, there we go.